Hey there, and welcome to the Mustang Math Tournament 2022 solution video. This video will have an array of some of what we think was the most interesting problems from the tournament from across the multiple rounds, and we encourage that if you haven't seen or attempted some of these problems before, to pause and try it yourself before continuing on with the video. Hopefully you enjoy. Let's take a look at number 18. In this question, we have a regular hexagon A, B, C, D, E, F, and a random point P which we choose in the interior. Now, if the probability that the area of quadrilateral ABCP covers at least half the area of ABCDEF can be expressed as a reduced common fraction A over B, let's again compute A plus B. So, let's first go ahead and just play around with where point P is, and we'll see how the areas come out. If we put P at the very center of the hexagon, then we'll see that this is clearly 1/3 of the total hexagon, as we can break it up into 3 parallelograms as shown. If instead P lands at some other point, then the area is some fraction of the total hexagon. We don't know what this fraction is yet, and we can determine that later. But now, let's say that P landed exactly on F, and it seems that the area of ABCP is exactly half of ABCDEF there. And similarly, if it landed on D, the area of ABCP would also be half. Now this seems like it would be really important because we're trying to figure out when ABCP is more than half of ABCDEF. So it seems like it would be useful to figure out when it's exactly half. I should clarify that technically D and F aren't actually in the interior of the hexagon, so P can't land on them. But the idea that we're using here is that P can get infinitely close to either of these points, so P is practically on D and F, and therefore our area will be practically half. So now, let's go back to the problem. If we examine how we calculate the area of ABCP, we can see that the area of ABCP is actually the area of two separate triangles. We can make these triangles ABC and APC. And this is useful because ABC's area never changes, it doesn't involve point P. So all we need to worry about is how the area of APC changes. So how does the area of APC change as we move P around? Well, let's remember back to our basic area formulas. The area of a triangle is the base of the triangle times the height of the triangle. If we set this base to AC, because it never changes, we can notice that the only thing that determines the area of this triangle is the distance that P is from AC. Therefore, if we wanted to find where P is a specific area, namely the area which makes ABCP half the area of ABCDEF, it would trace a line. And since we already have 2 points on that line, D and F, we know exactly what line this is. It's DF. So now, we can just notice that the points where ABCP is greater than half the hexagon is just all the points inside triangle DEF, because this is the region where the distance between P and AC is greater than the distance between the line AC and the line DF. So all we need to do here is to just calculate the area of DEF to the area of ABCDEF. So now, how do we do this? We can split this hexagon into 6 triangles with the same area. And even if they don't look exactly the same, we can see that all these triangles do have the same area. So we have these 6 triangles with the same area, so the area ratio is 1/6. And now, to get our final answer, all we have to do is add the numerator and the denominator, and we'll get 1 plus 6 is equal to 7 for our final answer. For our final bingo round problem, let's take a look at number 21. In this problem, Arpit the ant is looking for a path to get back to MMT-HQ. If Arpit only travels in the grid lines drawn below, and can only move left, right, and upwards, and never goes back to a point where he's already been, how many paths are there for Arpit to travel? So, looking at this problem, it seems like it's very complex and that there's lots and lots of moves that Arpit could make. So let's go ahead and try and find some conditions on this problem. First, let's suppose that Arpit moves up. He can't go back because he's already been to that point and it would be taking him down, but he can go up or to the right. If Arpit chooses to go up again, we'll have the same pattern, where he can go up or to the right but not down. Instead, let's suppose that Arpit moves to the right. at any one of these 5 points on this horizontal line, we will have to move up, so we go to the same state again. Another way to think about this is that when you're on a horizontal row, you can move left or move right as much as you want. It doesn't matter because as long as Arpit moves up, he will reach the endpoint eventually. He can either move up or continue to move left or right. Our goal here is to notice that the only move that affects his path of travel is him moving up. He can move left and right in either direction as much as he wants, but he is forced to move up eventually. So this means that there's 5 locations on each row where Arpit can choose to go up. He needs to pick exactly one of these 5 points for each of the first 4 rows in order to reach the top. Therefore, there's going to be 5 times 5 times 5 times 5 ways that Arpit will reach the top row. From this top row, there's only one way to go to get to the endpoint. Because he can't backtrack, he's forced to move right until he gets to the endpoint. Therefore, our final answer will be 5 to the 4th power, or 625. Now, let's take a look at the second question in the first part of the pressure round. Here, we're going to define the confused factorial of n as the arithmetic mean of n minus 1 factorial and n plus 1 factorial, where n factorial is n times n minus 1 times n minus 2, all the way to 3 times 2 times 1. We'll also note that 0 factorial is equal to 1. If we have the sum 1 confused factorial over 2 factorial, plus 2 confused factorial over 3 factorial, and so on until 20 confused factorial over 21 factorial, can be expressed as a reduced common fraction, a over b. Let's compute the value of a plus b. The biggest difficulties in solving this problem stem from the fact that we're using a new operation, the confused factorial, and also that the sum that we're trying to solve for is very long and difficult to work with. So first, let's rewrite this using summation notation, which is going to make the sum a lot simpler to work with because we can work with every term at once instead of individual terms. Next, let's deal with this confused factorial and split it into its definition, namely that n minus 1 factorial plus n plus 1 factorial divided by 2 is the same thing as the confused factorial. Now that we have this sum that's much easier to work with, let's go ahead and factor out this 1/2 constant from it, and then use the fact that I plus 1 factorial over I plus 1 factorial is just equal to 1. This is going to further simplify the summation. And now that we have this constant inside the summation, the 1, we can bring these outside of the summation. And because we have 20 terms, which each count 1/2, because we multiply the whole sum by 1/2, this will add a total of 10 to our final result. Now, let's reduce this fraction that's I minus 1 factorial over I plus 1 factorial. We can cancel out the I minus 1 factorial, and we'll be left with 1 over I times I plus 1. However, we don't quite know how to solve this, so let's transform it into something that we do know how to solve, using a technique called partial fraction decomposition. Using this technique, we want 1 over I times I plus 1 to be the sum of 2 fractions, one with a denominator of I, and one with a denominator of I plus 1. So, let's multiply both sides by I times I plus 1, and we get a degree 1 polynomial in I. Since this has to be equal to 1 for all I, the polynomial a plus b times I plus a minus 1 has to be a 0. So now we have the system of equations a plus b equals 0 and a equals 1. This is very simple to solve, and we can get a equals 1 and b equals negative 1. Therefore, 1 over I times I plus 1 is the same thing as 1 over I minus 1 over I plus 1. Now, let's go back to evaluating the summation. We can use this formula for 1 over I times I plus 1, and this actually gives us a telescoping summation. When we expand this, all of the minus 1 over I plus 1 and 1 over I terms cancel in pairs, except for the first and the last ones, namely 1 over 1 and minus 1 over 20 plus 1. So we can compute the result, and that will give us an answer of 220 over 21, which is equal to 241 when we add the numerator and the denominator. Next, let's take a look at problem 4, also from the first part of the pressure round. In this problem, Owen selects an ordered quadruplet of not necessarily distinct positive integers, we'll call them a, b, c, and d, uniformly at random, such that a times b times c times d is equal to 336. If the probability that at least one of these numbers is divisible by 14 can be expressed as a reduced common fraction a over b, let's compute a plus b. So, let's recognize first that a times b times c times d equaling 336 implies that the prime factorization of a times b times c times d has to be the same as the prime factorization of 336. It's also important to note that because a, b, c, and d are not necessarily distinct, all the combinations of prime factors are legitimate. So, for one of a, b, c, and d to be divisible by 14, its prime factorization has to contain both the 7 and at least one 2. So, let's go ahead and ignore the 3 completely and focus on the distribution of these 2's. So, because exactly one of these factors has to contain the 7 in its prime factorization, let's just assume that 7 divides d. It doesn't matter which number 7 can divide, so let's just assume that it's d. Because either 1, 2, 3, or 4 factors of 2 may be present within d to satisfy the statement, let's instead count the number of ways where there's 0 factors of 2 and subtract that from the total number of ways. So let's use the sticks and stones method, or the stars and bars method, and determine that there are 4 plus 3 choose 4 ways to distribute the factors of 2 within a, b, c, and d. We can also notice that there are 4 plus 2 choose 4 ways to distribute the factors of 2 within only a, b, and c. This is to say that d does not contain our factor of 2, and therefore d would not be divisible by 14. So, the number of ways to distribute the factors of 2 such that there is at least one 2 within the 7 is equal to 7 choose 4 minus 6 choose 4. So now, we can simply evaluate this and get 35 minus 15 equals 20 ways to distribute the factors of 2 such that at least one 2 is with the 7, which will mean that the factor is divisible by 14. We also know that the total number of distributions is equal to 7 choose 4 as well, so the probability is equal to 20 over 35, or 4/7. To solve the problem, we need to add the numerator and the denominator, and this will give us our final answer of 11. For our final pressure round question, we'll talk about the first one from the second part. In this problem, a lone uniformly selects two not necessarily distinct factors of 20 to the 22nd power. If the probability that at least one of these factors is divisible by the other can be expressed as a reduced common fraction, a over b, compute the value of a plus b. So just like the previous question we did, we can infer that prime factorization will be important in this problem as well. We're dealing with multiple not necessarily distinct factors. And here, let's go ahead and call those factors a and b. Let's break down 20 to the 22nd power into its prime factorization, which is going to look like 2 to the 44th power multiplied by 5 to the 22nd power. So first, let's consider the case where the two factors contain the same number of powers of 2. In this case, one has to divide the other, because no matter how many powers of 5 each one has, one will always have less than or equal to the same number of powers of 5, and therefore will divide the other. Because there's 45 different possible values for the number of powers of 2, the probability of this happening is 1 over 45. Next, let's consider the much more likely case that the powers of 2 in a and b are not the same. In this case, let's assume that the number of 2's in a are less than those in b, because it doesn't really matter which is larger. In this case, a has to divide b when it comes to the powers of 2 because it has a smaller number of those powers of 2. However, for a to divide b, we also need the number of 5's in a to be fewer than the number of 5's in b. So, similar to the previous case, if the number of 5's are equal, then the numbers will divide. So, there's a 1 in 23 chance that that will happen because the number of 5's can be anywhere between 0 and 22. If not, the probability of one being greater than the other is exactly half. One will be greater or the other will be greater. Therefore, the probability will be 1 over 23, that they're equal, plus half of 1 minus 123. Because first we have to get rid of the probability that the number of 5's is equal, and then multiply by 0.5. This will end up being 12 over 23. Now, let's combine these two cases and get the final probability of 1 over 45 from the first case, plus 44 over 45, which is the probability of the second case happening, multiplied by 12 over 23. This will compute to 551 over 1035. Because the question asked for the numerator plus the denominator, this will give us our final answer of 1586. Our last set of traditional problems will come from the Gallup round, and here we're going to look at the cycle round, where each problem's answer depends on another problem. We have to approach these somewhat differently than regular problems, and instead of solving one of these problems at a time, we'll have to try and simplify each answer and solve them in terms of each other. So first, let's take a look at problem 10, but keep in mind that we don't have the tools to solve it just yet. We'll need to work on each problem before we can have answers to any of them. So, for question 10, we have to let r be the answer to question 12. And Alice and Bob are running around two concentric circular tracks of radius 60r and 90r respectively, and they're both running at 3 units per second. If we assume that Alice and Bob run forever, we need to figure out the furthest distance that they will ever be from each other. Since r is dependent on the answer to number 12, we first want to find an answer to number 10 in terms of r, because we can't find what it is at the moment. We can draw these two concentric circles with radii 60r and 90r and select a point on the inner circle. As the two people are moving at the same rate and the lengths of their paths are different, they will eventually be opposite each other, which rids us of the possibility that the two people will never reach such a position relative to each other. Thus, the answer to number 10 in terms of r is just the sum of the radii, 60r plus 90r, which is 150r. Now that we've simplified question 10, let's go ahead and look at question 11. Here, we need to let a be the answer to question 10 and compute the cube root of the quantity of a times the cube root of the quantity of a times the cube root of the quantity of a, and so on. So, we do know that a is equal to 150r, but let's not substitute this yet, because it's going to make the equation a lot more complex. If instead, we set the cube root of a times the cube root of a times the cube root of a as n, we can then substitute n into itself, and this gives us the equation n equals the cube root of a times n. And by cubing both sides, we get n cubed is equal to an, and then n squared equals a, so n is the square root of a, or the square root of 150r. At this point, we have both question 10 and question 11 in terms of r, which is really good. So let's move on to question 12. In this question, we let n be the answer to question 11. And in the regular polygon a1 through an, let's compute the degree measure of angle a1, a6, an. So, since we know that a1 through an is a regular polygon, this polygon is also a cyclic polygon. By the inscribed angle theorem, we know that angle a1, a6, an is half of the measure of minor arc a1, an. And as there are n minor arcs of that same measure because a1 to an is an n-sided polygon, the measure of a1, a6, an is 360 over 2n, or 180 over n degrees. So substituting n for the values found in the previous questions, we get that r is equal to 180 over the square root of 150r. Now, using this answer for question 12, we can solve for r. Let's go ahead and square both sides to get r squared equals 180 squared over 150r. This is equal to 32,400 over 150r. We can simplify this and get 216 over r. Here, let's go ahead and multiply by r again and get the r cubed is equal to 216. Now, all we have to do is take the cube root of both sides and get the r is equal to 6. Now that we have r, all we have to do is substitute this value into the previous questions. So for number 10, we have 150r. So 150 times 6 is equal to 900. For question 11, the answer in terms of r was the square root of 150r. So we plug in r equals 6, and we get the square root of 900, which is 30. And that's our answer for question 11. For question 12, we already had the answer because r equals 6. So with this, we're finished with the problem. For For the last question we'll do together, let's take a look at one of the hardest puzzles on the Mounting Mayhem round. This is a variant of Polyamino called Polyamino. And the rules of this puzzle match that of regular Polyamino, except that every shape, or polyomino, that exists in this grid that we have must have exactly one pal somewhere else in the grid that's congruent to it. One of the first things we can notice in this puzzle is that there's 10 unique 4s on this grid, and none of them are close enough to each other to take up the same piece or to merge with one another. This is because any of these connections between the 4s would take up more than 4 squares. Let's go ahead and call this the merger rule, and we'll use this multiple times throughout solving this problem. The polyominoes that we're currently interested in have 4 squares, so let's go ahead and call them tetraominoes. Let's consider the possibilities for what these tetraominoes might look like, and we'll find out that there's exactly 5 possibilities, and you might be familiar with these if you've ever played the game Tetris. These are the square tetraomino, the T tetraomino, the straight tetraomino, the L tetraomino, and the skew tetraomino. Following the rules of Polyamino, since each shape must be used exactly twice, we now know we have 2 of each of these shapes in our grid. Now that we've determined what shapes these tetraominoes might take, let's take a look at the 4 that's in the bottom left corner. Let's first notice that the 4 has to extend out at least 1 square to the right, because there's a 1 right above it. Now, let's also consider the possibilities for where the last 2 squares of this tetraomino might go. Let's remember our merge rule, and see that many shapes, such as a straight tetraomino or a skew tetraomino, can't be there, because they would touch another 4 and therefore would have more than 4 squares. So, the only possibility here is to create a T-piece that narrowly avoids contact with both of the other 4s. Looking at the 4 in the bottom right, we'll see that we have this exact same situation, so we'll have another T-piece in the bottom right. This also helps us because now we've used both of our T-pieces, so we can't have any more in the rest of the puzzle. We'll also notice that this forces the 2 next to it upwards into the empty space. Now that we've found where all the T-pieces go, let's focus on the 4 that's in the bottom middle. Again, we'll see that it has to extend at least 1 square upwards, so it doesn't merge with the already set T tetraominoes that are on its left and on its right. As it turns out, the other 2 squares of this tetraomino are also very restricted. See how it extending left or right will force us to either create 2 1s or break the merge rule. Since having 3 1s is not allowed, we can only go upwards, and this leads to a straight tetraomino. Now, let's focus on the 4 that's on the right. For this one, there's 3 possible configurations for this tetraomino that wouldn't break our merge rule. But of these, we already have 2 T tetraominoes, so we're down to 2 cases. Let's consider the case that's an L tetraomino. We'll see here that extending to the left would block in the 6, and the 6 would only have room to form a pentomino, or one with 5 squares. Therefore, this tetraomino has to extend upwards to form our other straight piece. Now, let's go to the other side, and here we also have 3 possible pieces, the L, the T, or the straight tetraominoes. Of these, we've already used both of our T's and both of our straight tetraominoes, so this one has to have an L. And with this, we can also fill in the 5. Next, let's focus on the rightmost 4. And here, let's refer back to our merging rule, and we should see pretty clearly that the only possible tetraomino here is the L. And now that we've used up all L's, all T's, and all straight tetraominoes, the only remaining shapes we have to work with are the square and the skew tetraominoes. So now, let's turn our attention to the 4 that's on the left. The square tetraomino clearly doesn't work here. It would break the merge rule with the one on its right, so we must use a skew piece as shown. Similarly, if we take a look at the center 4, using a square tetraomino will break the merge rule, so we have to use our final skew tetraomino here, which allows us to extend our piece at least 1 up. But we don't know whether this goes left or right. However, this does mean that our 2 remaining 4s will be the square pieces, so they extend at least 1 space down. We've done all we can for the 4s, so let's go ahead and step away from thinking about the 4s and instead look at the 3s, or triominoes, that we have in this puzzle. We'll see 3 different 3s that once again are subject to the merge rule. So we can use both possible triominoes in this puzzle, the straight one and the bent one. Let's look at the 3 on the right first, and we'll notice that it can't extend 2 squares to the left as it would merge with the 3. Thus, it has to extend at least 1 square upwards. This makes it so that the tetraomino in the upper right corner must extend left, and this will allow us to complete that tetraomino. Now that we've filled in a bit more of the grid with triominoes, let's take a look back at the 4s, and specifically the 4 that's in the middle. As we said earlier, this has to be a skew tetramino, and we can now see that it can't skew to the right, as this would force the 3 that's next to it to break the merge rule. Therefore, this tetramino has to skew left. And this is also interesting because it creates a situation with the 6. We can see that even if we fill in as much space as we can, the 6 is forced to go at least 2 spaces upwards, and this will force the square tetramino to go to the left, and allows us to fill in the bent triomino. So we filled in a lot of squares with just this one situation. Now we come to the most difficult part of this question. By counting all the squares that we've accounted for, we'll see that we have the single monomino and its pal, the domino and its pal, the 3 visible and 1 hidden triomino, the 10 tetraminos, the 2 pentaminoes, and the 2 hexaminos. We have exactly 80 squares that we've accounted for, which means that the unaccounted hidden polyaminos have to be exactly 2 pentaminos. So, let's look at these 2 6s or hexaminos that we've started on this board. We know that these have to be pals because we've determined that they're the only hexaminos on this board. So, after some experimentation, we can see that there's only one arrangement with which we can fill in both hexaminos without also causing more than one stray monomino. Once we find this one possibility that works, we also find the pal for our monomino. With this, we're almost done. We need to find space for a pal for the complete pentamino that we have in the bottom left. We'll see that if we try to place it in the 1 orientation that involves the 5 at the top, the 3 next to it is once again forced to merge with the other 3. Therefore, the pal for this pentamino must be in the perfectly shaped cavity that's on the right side of the grid. And additionally, since there's not enough space for 2 pentaminos at the top of the grid, the 4th pentamino has to be in a cavity that's on the left. Now, we still need to find space for our 2 straight triominoes. We'll notice that there's no space for this 3 to be part of a straight triomino. That means that the partial one on the right is straight and extends 1 upwards. Also, the only other space for a straight triomino that leaves enough room for the other triomino is horizontal at the very top. Then, we can extend the 5 into the cavity on the left, which forces it into the p pentamino shape at the top, and we can fill in the rest of the triomino and our last hidden domino to complete the puzzle. We hope you enjoyed these problems and found the solutions we devised interesting. As usual, if you have your own solution to a problem, go ahead and send it in the comments or reach out to us on Discord. We always love discovering new and unique solutions. Also, if you want to explore more problems like these, go ahead and check out our website at www.mustangmath.com and consider participating in our future competitions, classes, and events. Until next time.